This is an online presentation for the SAE Noise and Vibration Conference held in Grand Rapids, Michigan, September 2021. My name is Mark Every, and I'm presenting this with my colleague from the acoustics team at BlackBerry QNX, Joel Desiel. Today, we'll talk about a streamlined workflow for designing vehicle sounds for rapid deployment and tuning in embedded production systems. We'll split the presentation into two parts. Firstly, I'll discuss the process of designing sound for vehicles, and then I'll hand over to Joel for a live demo of our software design tools. The scope of this presentation includes interior and exterior engine sound design, including active noise control for all vehicle types, AVAS for EVs, or acoustic vehicle alerting systems, and vehicle chimes. We are proposing a streamlined process for automotive sound design for any of these applications that reduces the number of design iterations and time to market, supports driving simulation in the absence of vehicle prototypes, and uses software that is available today. Let's start by summarizing the existing process for vehicle sound design. Of course, there are some variations between manufacturers in the process, but typically it goes something like this. We have an initial sound design concept phase where the sound designer will work with a digital audio workstation like Pro Tools or Logic, or a graphical programming environment like Max or Pure Data to design a number of concept sounds. Once a concept sound has been approved either by management or through subjective listening tests, the next stage of the process is to implement this concept sound on production hardware. This typically involves some writing or porting of signal processing algorithms, some optimizations to meet the memory and CPU budget of the system, and if we're lucky, we're able to achieve an embedded implementation of our concept sound that is subjectively close enough to the original concept sound. If that's the case, we proceed to the third stage, which is the in-vehicle tuning. At this point, we hook up the live vehicle parameters such as RPM, throttle, engine load, and so on to the synthesis algorithms and play back the synthesized sound through the vehicle speakers. We'll also need to adjust the overall EQ and gain, make sure the synthesized sound is spatially reproduced in a pleasing way and is sufficiently responsive to the driver's input. If everything goes well, we're ready to move to production. So, what is the issue? In practice, this is a highly iterative process with many possible points of failure that can take many months to complete. Let's start with the first phase, where we design the concept sound. Unless the sound designer is working with real vehicle data and can audition the sound in the presence of the primary engine noise and other noise contributions in the vehicle, such as road or wind noise, it's extremely difficult to predict how well the sound would be perceived in a real driving scenario. So the sound designer is in a sense working blindly. Secondly, the perception of designing sound over headphone playback is very different from the perception of being in a vehicle. For example, an engine sound that sounds very powerful and impressive when listening over headphones may sound obtrusive or tiresome when the driver is exposed to this sound for a long duration whilst cruising down the highway. In the second phase, another set of challenges faces us. Is the concept sound actually realizable in real time? For example, can it be implemented with low enough latency? Or did the sound designer, for example, make use of filters that add significant perceivable delay? Can the concept sound fit in the CPU and memory available on the target system? For example, a convolutional reverb algorithm might be a great addition to the concept sound, and many PC and Mac software apps offer this type of functionality, but it's a very CPU and memory intensive algorithm that might not run on the target system depending on its specifications. Similarly, if you're using a lot of source audio data in the concept sound, you can easily run out of memory. Lastly, does the manufacturer even have the skills necessary to port the synthesis algorithms to the target? If the answer to any of these questions is no, we return to the first phase. In the last phase, we finally hear our concept sound in the actual vehicle. If you manage to get it right the first time, you're extremely lucky. Normally the sound design will go through several iterations before it is tuned such that it fuses well with the existing primary engine noise and other noise sources, is responsive to the driver's input, and also meets a certain threshold of plausibility. What I mean by that is that the driver does not perceive the sound as obviously synthetic, but rather as an extension of the physical vehicle and drivetrain. The perception of spatial envelopment of the sound using the vehicle speakers is an important aspect at this stage, and one that is hard to design for in any prior phase. Of course, with AVAS, the design goals are a bit different and more focused on meeting the regulatory requirements. It is a very real possibility that the concept sound simply does not work in the vehicle, and then we're back at square one. Okay, so let's now talk about how to streamline this process. But first, I have to raise another consideration, which is the availability of prototype vehicles. We consistently hear the message that fewer prototype vehicles are being produced than ever before to streamline the entire vehicle production process. And manufacturers see the need to shift to simulation before prototypes are actually built to counter this. So I'll break this down into two proposed processes. The first is the traditional model using a vehicle prototype, and the second relies on simulation. Firstly, our streamlined process has 2 stages instead of 3, and starts with the software integration stage. However, some of the exploratory work in phase 2 could actually happen in parallel. We start by porting the QNX Active Sound Design library to the target system. This is a C library that requires a floating point capable processor and is suitable for almost all the SoCs and DSPs that are commonly used in automotive today. So it is generally quite a straightforward process to build the library for the target system. We'll also implement a client-server interface that allows the Windows-based tuning tool called LiveAmp to talk directly to the AST library over an Ethernet or even serial port. The AST library has an extensive toolbox of synthesis and effects modules, which can be configured into a user-defined audio flow, which Joe will demonstrate. Wave files can be brought into ASD from other software tools, such as from a digital audio workstation, or the engine sound can be synthesized completely from scratch. The possibilities for sound design are endless, and we still find ourselves finding new and creative ways to use the toolbox. In the second phase, there's no clear distinction between a concept sound design and the final in-vehicle tuning. The engine sound can be designed in the vehicle itself, or alternatively at a desktop using real data recorded from the vehicle, and this would include reference microphones containing the other noise source contributions. The same AST library is used in both cases, so the same synthesis capabilities are available in both environments. A concept sound design at the desktop can be pushed to the target system in the vehicle with the push of a button and immediately auditioned in vehicle. So now let's return to the situation where a prototype vehicle is not available. In this case, the final tuning of the production vehicle must be as short as possible and it leaves little room for error. So the exploratory sound design phase must happen in simulation. We're excited to announce 2 important partnerships. Firstly, we've integrated QNX Active Sound Design into VI-Grid's simulated vehicle powertrain and noise environment. Secondly, we have integrated AST into the Presense NVH simulator from Head Acoustics. Driving simulation includes the simulation of vehicle data, for example, RPM, throttle, and engine load, based on simulated driver input, and accurate simulation of other noise source contributions, such as primary, engine noise, road, and wind noise. So at the end of this phase, we can be fairly confident that our concept sound will work well in the final production vehicle. In phase 2, the integration needs to happen like in the previous slide. Finally, in phase 3, some in-vehicle fine-tuning is expected, such as tuning the overall gain and EQ, and some spatial characteristics. I'm now going to hand over to Joel, who's sitting in a vehicle right now, connected to AST, running on a Raspberry Pi with QNX real-time operating system.
Hello everyone, this is LiveAmp. Right now I'm actually sitting in one of our test vehicles and I've got a Raspberry Pi next to me with the QNX operating system on it, and it is connected to the vehicle with a CAN bus reader. So I'll go ahead and connect to the Raspberry Pi. LiveAmp is actually used to control most of our acoustic products at QNX, which is what these other icons are for. It also gives us a basic idea of the signal flow through the system. And all of these targets, we can actually access the audio that's running through the system at different points. So we can listen to it or record it to a WAV file, even actually replace the audio with our own recordings if we'd like to create reproducible tests, and of course monitor level meters and the frequency spectrum. On the right here you see I've got already some inputs set up that I want to receive from the vehicle. So if I actually turn the car on right now, we will see the values come to life. Press the gas here. Now, I'm not going to leave the car on for the demo, but that's alright because I do have this override checkbox here. Whether I'm connected to the car or not, I can always just override the values and directly set the RPM, throttle speed, whatever inputs I've set up. So going into the active sound design section. So these settings were already all on the vehicle, but I'm going to open up a project file as well, just so that as I work, any changes will also be saved to my laptop. We start off with our library setup information. We can set the number of channels. Right now I'm connected with a USB sound card to the Raspberry Pi that has the ability for up to 2 microphone inputs and 8 outputs. I've got 6 set up right now. The system actually allows all the way up to 32 outputs if you actually have a sound card that can support that and you need that many outputs. If engine order reduction is enabled, also known as active noise cancellation, you can set which output channels the cancellation signal is outputting on and also which engine orders that you want to cancel. We can actually cancel orders from 2 separate RPMs. It doesn't have to be just the one setting. Over on the Vehicle Inputs tab, this is actually where I get to define all of the data that I want to get from the vehicle. Everything on this left column is something that I'm getting right from the CAN bus. And then everything else is how I can manipulate or massage that data. A very common thing to do would be to smooth out the values. Maybe if you have a driver that stomps on the gas pedal and you have that linked to a volume of some sort, maybe you don't want such a quick jump in gain, so you could smooth out that value by adding on one of our smooth values here. Now, another common one would be to work with the linear object. This one lets you basically map one value to another. So if I take a look at this one, we'll see that speed was brought into a linear box, and that has essentially converted it into a simulated RPM just by setting whichever values you want on this curve. This one's fairly limited, but you can go from 0 to 32,000 if you really want, and you're going to have many points in here as well. It doesn't have to be just a straight line. We also have some low frequency oscillators that generate their own values, and that can let you create some really cool effects. On the Calibrate EOR page, this is where we perform an in-situ calibration of EOR to measure the secondary path from each loudspeaker to the microphones. I can also visualize the calibration by just downloading whatever is currently being used on the target. On the Tuning EOR page, this is where we set up our various parameters to control how much is being canceled and how much we want to limit the cancellation signal. I can also enter a logical expression to decide when the EOR is enabled, such that I can shut it off if a door or the trunk is open. I can also set things like frequency range and the convergence speed of the system. Now moving on to the modules section. Let's bring back this frequency spectrum display. We'll use it later. This is where most of the sound design actually happens. One of our sound designers set up this interesting patch where there's only one noise source and it's being filtered through many modules to create a very cool effect. Why don't I just turn on one of my presets here. So now we can actually hear what the output of the patch is doing, and I'll override my values. Just mute that for now. All of that sound from just filters, and there's a final signal chain right here if I scroll over, where he has broken it out to various channels to create a stereo widening effect here. Of course there's reverb added on and a bunch of filtering and gains depending on what gear we're in. We have a lot of different modules to choose from. There's noise, tones for creating different shapes like triangle or square waves. You can even do shepherd's tones in there. Additive and granular synthesis, of course. And the sample player. Sample player is very helpful for if you have a sound designer that wants to work outside of LiveAmp in a digital audio workstation and do all their sound design that way. I can just drop in a sample player or many sample players and load in a file. This is just one that I grabbed from a free database on the internet. All I need to do is just press this one quick button. I've now uploaded that file to my Raspberry Pi. I'll just hook it up into this mixer for ease. And why don't I go ahead and actually just temporarily disable my noise source, reinitialize so that the Raspberry Pi has that new module I've added. And we'll put back on our listen here. So here we're just listening to a loop, that looping sound. There are some settings, of course, in here. I can choose, again, to use a logical expression to decide when it turns on, or a more common setting here would be to change the pitch. I've just changed it to adaptive, so I can set it to something super obvious. We can hear a change. I can have this pitch change based on any of the inputs that are set on that input tab. Right now it's set to real RPM, so if I override my values and just move that RPM, we will hear the pitch change. Close that and just disable it for now. There are a lot of modules to choose from. Those are all our sound sources we talked about. There's of course gains, adaptive gains, so you can change the volume based on, say, the throttle or the speed. Many different filters, as you can see, there's several here. All of these filters are adaptive as well. So this, if I just open up a random one, I can see this simulated RPM is being used to change the center frequency of this bandpass filter. You can also, just set a fixed frequency if you want, or lock it to an engine order. So as the car is driving, the center frequency will adapt up or down based on whatever the current RPM is. And there are other effects, fun things to play with, like distortion, flangers, reverbs, stereo widening to create a better sound field inside the vehicle. Another feature to talk about would be our analysis page. This is where I can load in the recording of an internal combustion engine vehicle. We can see the engine orders on display here in the frequency spectrum, and the system can track these values, and we can use it to extract the amplitudes over RPM and apply it to additive synthesis, so we can recreate this engine using only sine waves. Or we can use it as part of the granular synthesis module and actually play back any point in the file based on the size of a perfect engine cycle, so that there's never any pops or clicks. The last tab in LiveAmp here is our chimes designer. This of course is for creating chimes and safety alerts. You can design a sound by placing sine waves, and it will actually output a wave file that is the absolute shortest necessary to achieve the set of sine waves that you've set up. That way you can then put it into one of the sample players on the modules tab and apply an ADSR amplitude envelope to create a chime using the smallest amount of memory on the system, in case your system is restricted memory-wise.
So I hope it's clear now that you can design engine sound, active noise control, AVAS, and vehicle chimes on a production system in real time in a user-friendly application and immediately hear the results in the vehicle. Thank you very much for your attention, and please reach out to us if you would like any more information.